Hello everyone, I am Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss some questions based on electric and magnetic materials. So that will be a question bank on electric and magnetic materials. So before seeing the questions, let us see the assessment pattern. So when it comes to assessment of this particular course, Applied Physics, I'm talking about the course. Applied Physics, we have two types of assessments. The first one is internal assessment. Internal assessment, which is for 30 marks. In internal assessment, we have two things. One is continuous internal evaluation. Continuous internal evaluation. In continuous internal evaluation, we have two, CIE 1, which will be for 20 marks, and CIE 2, which will be for 20 marks. There are two continuous internal evaluations. These will be theory. And then we have alternate assessment tools. Alternate assessment tools. We call it as AAT. AAT stands for alternate assessment tool. So in alternate assessment tool, we have concept video, for 5 marks, and tech talk for 5 marks. So the total put together will be for 10 marks. Here each CIE is scaled down to 10 marks and the total we are getting for 20 marks. So 20 plus 10, we have 30 marks will be the internal assessment. And then we have the external assessment. Which we call it as semester end examination. This is semester end examination. Which is SEE. This is for 70 marks. So 70 marks is for external and 30 marks will be for internal. So now let us see the pattern for CIE and SEE. So CIE pattern is you will be writing an exam for 20 marks in the first 2.5 modules. First 2.5 modules you will have for CIE 1. And here you will be answering any 4 questions out of 5 questions. Any 4 out of 5, and each question carries 5 marks. So 4 into 5, 20 marks. So each question carries 5 marks. Any 4 out of 5, so we'll be having choice here. And how will be the questions here? First question, A part will be theory for 2 marks and B part will be analytical. in all the questions, A part will be theory and B will be analytical. Theory question for 2 marks and analytical question for 3. So put together 5. That is what I said. Each question carries 5 marks. So like this you will get 5 questions. A, B. Every question has 2 parts. A and B. Theory as well as analytical. So this is for 5 marks. Each question is for 5. And most of the times, these 2 questions, first and second, will be from module 1. And 3 and 4 will be from module 2. And this will be from module 3. You are going to get only 1 question from module 3 because we are covering only half the part of the module. So this gives a clear idea for you in preparing for the CIE. So 5 questions are given, out of which you have to answer 4. So that scores 20 marks for you. Now coming to the SEE, semester end examination, you will have all the 5 modules. The duration of the exam will be for 3 hours and the marks are 70 marks. Here you will be having 1 question from each module. You will have to answer 1 question from each module and all questions carry equal marks. Each question carries 14 marks. Each question carries 14 marks and there will be an internal choice inside the module. For module 1 and 2, you will be given only one question where there will be no choice. But for module 3, 4 and 5, you will be given 2 questions out of which you can answer any one. But from each module, you will be answering 1 question and each question carries 14 marks. And also in each question, again, there are 2 parts. A, which is a theory question for 7 marks, and B, which is an analytical question for 7 marks. So A is for 7 marks and B is also for 7 marks. So put together 14. So 14 into 5 questions you are answering will get 70 marks. So this is the pattern for SE. Now coming to the question bank. So if you see in your learning portal, you are given the question bank which consists of a set of questions from each module. So each module will have questions in 3 parts. So part A, you have analytical questions. Analytical questions in part A, maybe 10 in number will be given, 10 number analytical questions. And part B is long answer questions. Part B is long answer questions. So long answer questions are generally questions of 7 marks weightage, which you see in SCE exam. And they will be 20 in number. And part C has short answer questions. They are short answer questions, which are 20 in number. So total from each module you will be given 50 questions. These 50 questions will give you a very clear idea of what type of questions will be asked in CIE as well as SE. So with this we move forward to discuss the questions. So first we will be discussing the short answer questions. Short answer questions, that is part C. So when you see the question bank, you will see this questions in this format. The first question, you will have the question here. Explain different types of solid dielectric materials and their polarization process. Now, this second column denotes what level of learning it is. We call it as Bloom's taxonomy level. This is Bloom's taxonomy level. This helps us to understand the level of learning the question needs. So when I say here understand, it is understanding level. Generally, we have remember, understand, and then apply. These are the three levels of questions which you will be asked at the first year level. And this next column, it talks about the prerequisites. To understand or answer this question, what are the prerequisites? What do you have to know before? So you will have to recall different types of materials and then understand the nature of polarization. And the last column talks about the course outcome. So course outcomes are generally the outcome which is mentioned when you are learning this topic. What will be the outcome? What will the student be able to do after learning this? That is what we call it as student outcome or the course outcome. Now, when I am discussing the questions, I will be discussing the questions one by one, and I will not be talking about the other parts. That is for understanding. Now, the first question is, what are the types of dielectrics? So, when it comes to the type of dielectrics, we have two, polar and non-polar. Two types of dielectrics we have. Polar dielectrics and non-polar dielectrics. So what are polar dielectrics? So when we consider polyatomic molecules, the center of gravity of the negative charge distribution may not coincide with the center of positive charge distribution. Means if I take the center of gravity of the positive charge like this and the center of gravity of the negative charge like this, they are not coinciding with each other. They are separated by a distance. There is a separation between the centers of the positive and negative charge distribution. Then we call it as polar dielectrics. And whenever there is a separation like this, in a polar dielectric, there will be net dipole moment. That is why we call them as polar dielectrics. There will be a net dipole moment. Coming to non-polar, means which are not polar in nature. So generally, monoatomic materials are made up of such atoms. So in non-polar dielectrics, what we see, the center of gravity of the negative charge and the center of gravity of the positive charge coincide with each other. Means if this is the positive charge center, this will be the negative charge center. These two are coinciding with each other. So then what happens? They are not separated. Because they are not separated, the dipole moment will be zero. So for a non-polar dielectric, the dipole moment is zero. So those materials whose dipole moment is zero, we call them as non-polar dielectrics. Now coming to the phenomenon of polarization. What is polarization in dielectrics? So when we are applying an external field, the dielectric polarization is the term which is used to describe its behavior. Means how the material behaves in an external field. So what happens when we are placing a dielectric in an external field? Dipole moment is developed. Dipole moment is developed. How these dipole moments are developed? Because of the separation of charges. How the charges are getting separated? Due to the electric field that we have applied. So let us see how it is formed. Now we have a electric field that is applied. Means we have connected this to the positive and this to the negative. So we have a positive plate and a negative plate. Due to this, we have an electric field. So in this electric field, when we place a dielectric material like this, then what happens? All the negative charges will get aligned onto this side and the positive. So what is happening here is the separation of the charges, giving rise to dipoles, which give rise to dipole moment. So this is what we call it as dielectric polarization. So this is happening due to the shifting of the charges, the charge distribution, which is shifting due to the applied electric field. We are getting the polarization. Now coming to the second question, write the Lorentz relation for internal field or local field of a dielectric material. So we are going to write this Lorentz relation. Lorentz is the name of the scientist who has given a relationship for the internal field or the local field that is developed in a dielectric when it is placed in an external field. So what is the local field or electric field? EI or E local. We may represent it as EI or E local, which is equal to E1 plus E2 plus E3 plus E4. Here, E1 here is the external field that we are applying. E1 is the external field. And E2, it is the field that is developed due to the displacement of charges onto the surface of the material. Field due to charge separation, on surface of the dielectric. And E3 is if we are taking a small spherical cavity inside the dielectric, so all the dipoles are arranged in a random motion and the dipole moment will be 0. So therefore, E3 is generally 0, which is due to the dipoles inside the spherical cavity. This is due to the dipoles inside the spherical cavity. And we have E4, which is due to charge on surface of the sphere. So this spherical cavity is also there will be separation of charges, and because of that there will be an electric field which we are calling as E4. So now generally E3 is equal to 0 because they are in random motion and they cancel out, and the net electric field is 0. EI, the contribution will be from E1, E2 and E4. Now we have taken E1 plus E2 is equal to E. Generally E1, if this is in this direction from positive to negative, now the induced field on the surface will be like this, negative, positive. So it will be in the opposite direction. This is E2. So what will be the resultant due to the 2 is E is equal to E1 minus E2. That is given as E. And EI is equal to E plus E4. So whatever we have is E is equal to EI plus E4. And what is E4? P by 3 epsilon naught. P here represents the polarization. P is the polarization. And epsilon naught here is permittivity. It is the permittivity of free space, that is air or vacuum. So the final expression for EI I, that is E internal or E local, is given by capital E plus P by 3 epsilon naught. Now the third question is, ferroelectrics and dielectrics, how are they different from each other? So if you see by nature, dielectrics and ferroelectrics are insulators. They are insulating materials. But the polarization and the displacement vectors are given by P is equal to epsilon R minus 1 into epsilon naught E. That is chi epsilon naught E. And epsilon naught epsilon R E. So for dielectrics, if you are talking about dielectrics, both the properties chi and E, epsilon, they are field independent, means they are not dependent on the applied field. But when we talk about ferroelectrics, chi and epsilon are dependent on the field. So that is the major difference between dielectrics and ferroelectrics. Now coming to the Clausius-Mosati relation. Clausius-Mosati relation. So Clausius and Mosati are two scientists who has given us a relationship between the macroscopic and the microscopic quantities that we have in polarization for a dielectric material. So what is the relation given by them is epsilon R minus 1 by epsilon R plus 2 is equal to N alpha by 3 epsilon naught. So here epsilon naught is permittivity of free space, microscopic quantity. These two are epsilon naught and epsilon R. Epsilon R is the relative permittivity. It is a relative permittivity. So this is equal to what? N alpha by 3 epsilon naught. Alpha here represents the polarization vector or the polarization constant, we say. And N here is rho Na upon M. The value of N is what? Rho Na upon M. What is rho here? Rho always represents the density. And Na is the Avogadro number of atoms and capital M is the molecular weight. So if you know these values, you can get the value of capital N. So epsilon R minus 1 by epsilon R plus 2 will be rho Na by M into alpha M by 3 epsilon naught. We are writing alpha M in specific because it represents the molar polarization. That is why we are writing alpha M. Now the next one is, what are the types of polarization we have? Types of polarization. There are 4 types of polarization. What are the 4 types we have? Electronic polarization, ionic polarization, orientation or dipolar polarization, and then space charge polarization. Electronic polarization is due to the separation of the positive and negative charges. And ionic polarization is due to the separation of ions, positive and negative ions in an ionic dielectric. And orientation is due to the orientation of the dipoles. We have polarization. And the space charge, because of the space charge that is produced, which is mostly negligible. Now the next question is, when an electric field is applied, how does the phenomenon of polarization takes place? So we have seen the types. Now we are seeing the process or the phenomena, how polarization occurs. So how is the polarization mechanism? So when an electric field is applied on a dielectric medium, all the positive nuclei of the atoms move in the field direction. Means they start moving in the direction of the field. And the negative electron cloud will move in the opposite direction. So how this movement is happening, we'll see, understand with the help of this figure. So when there is no field, when there is no applied field, E is equal to 0. Then the positive, the center of gravity of the positive charge may be coinciding with this. The distribution of the charges is like this. But when we are applying an electric field is applied. So on applying the field, what happens? The positive charges is shifting, moving towards the field, and the negative charge in the opposite direction. So like this, there is separation or distribution of charges. So because of this distribution like this, there are dipoles that are formed. And whenever we have dipoles, there is dipole moment. So because of polarization, dipoles are formed, which gives rise to dipole moment. Now the electron cloud shifts towards the positive end, we have seen. And the shift of electrons is always proportional to the field strength. So whenever we are talking about the applied field, as the field strength increases, we can write the magnetization or the polarization here will be proportional to H. So more the field strength, more the shift. The shift is always proportional to H. H here is the applied field. And the dipole moment is the product of charge and the shifting distance. If we are representing the dipole moment by mu, mu is equal to Q into R. Mu is equal to Q into R means the dipole moment is the product of charge and the separation between the charges. Whatever the shift that has occurred, we are writing it as R. Now explain what is local field and external field. So we have to explain about the local field and external field. So the field E1, if you are seeing the figure here, we have a field that is applied. So how we are applying this field? We have taken an external supply. This is the external supply, positive and negative. We have connected the positive terminal to this plate. So this will be positive. And we have connected the negative plate to this. So this is negative. So positive and negative. So this gives rise to the field, applied field E1. So what is E1 here? E1 is due to the external applied field. Now comes E2. E2 is due to the induced charges on the dielectric sample near the surface. So what is a dielectric sample here? This is the dielectric sample we are putting in the electric field. We have the electric field like this. Now in the field we have placed this dielectric. Now what will happen on the surface of the dielectric? There will be charges that are deposited. Negative onto the positive plate, on the side of the positive plate, and positive on the side of the negative plate. So this is how the charges are separated. This is the separation. And because of this, there is a field. This field, we are calling it as E2. E2 is due to the charges induced on the surface of the dielectric. Then we have E3. E3, that is due to the dipoles inside the sphere. Now if you consider this sphere, this is the sphere or the spherical cavity which we are considering inside the dielectric. There will be a number of dipoles inside which are oriented in random directions, and because of which the dipole moment will be, or the net dipole moment will be 0. So the electric field E3 will be 0 because of the crystal symmetry also. So E3 is equal to 0. And then we have E4. E4 is due to the polarization of charges on the surface of spherical cavity. So this is the spherical cavity we have, and this is the charges that are induced on the surface of the spherical cavity, positive here and negative here. So the total internal field now is given by E1 plus E2 plus E3 plus E4. So E1 is the external field and EI or E local gives the internal field. Now coming to what are polar molecules and what are non-polar molecules. So first we'll see what are polar molecules. Polar molecules, they have unsymmetrical nature. They are not symmetric. Because they are not symmetric, they have a permanent dipole moment. So two things, unsymmetrical in structure and having an permanent electric dipole moment. So what are the examples of these polar molecules? H2O, water, HCl, CO, N2, NH3. All these are examples for polar molecules. Now let us understand the electric dipole moment with the help of one example. So we'll take water, H2O. So when we take water, this is the arrangement. It is not symmetric. So this is a hydrogen molecule, H and H, and O we have water molecule in which we have two hydrogens and one oxygen arranged in this fashion. So H I take as positive, this is negative. And the dipole moment is always directed from positive to negative. So this is the direction of dipole moment between this H and O. Now for this H and O, again it is directed from positive to negative, from here to here. So both are directed towards O, and there will be a net dipole moment which is given by 1.84 D. The dipole moment mu is equal to 1.84 D. So whenever we are considering a polar molecule, the net dipole moment is not equal to 0. So this is the structure for NH3, HCl, and then CH3, Cl. Now coming to non-polar. What are non-polar molecules? So first thing is they have symmetrical structure. They are symmetrical in structure and they have zero dipole moment. This is the comparison between the two. They are unsymmetrical and they have a permanent dipole moment. But when it comes to non-polar molecules, they are symmetrical and they have zero electric dipole moment. Why they are having zero electric dipole moment? Because the positive charge may be concentrated at a point which we call as the center of gravity of the positive charge. And if the center of gravity of the positive charge coincides with the center of gravity of the negative charge, when these two centers coincide, two centers of gravity coincide. Which two centers? The center of gravity of the positive charge and the center of gravity of the negative charge or the negative electron cloud. When they are coinciding with each other, the net dipole moment is 0 and we call it as a non-polar molecule. Next one is, what is the relationship between susceptibility and dielectric constant? We are going to understand the relationship between susceptibility and dielectric constant. So first, let us see what is susceptibility or electric susceptibility. So it is defined as the ratio of polarization vector P to the electric field E, intensity of the electric field E. So chi here represents the susceptibility. So it is the ratio of what? Polarization vector P to the electric field E. And epsilon naught here is the permittivity of free space or vacuum. And we know the formula for P. P, the polarization vector, is given by epsilon naught into epsilon r minus 1 into E. So if you are substituting that here, epsilon naught into epsilon r minus 1 into E by epsilon naught E, these two get cancelled. And we are left with only epsilon r minus 1. So chi is equal to epsilon r minus 1. What is epsilon r here? It is the dielectric constant. It is also called as relative permittivity of the medium or dielectric constant. So this gives us the relationship between susceptibility and dielectric constant. Now coming to the 10th question. Why is a capacitor known to be an energy storing device? Why we are calling a capacitor as an energy storing device? So what we see here is they are used to store electrical energy in the form of electric charge. So whenever we are talking about a capacitor which has two plates which are separated by a distance D, and whenever you are taking a positive plate and you can bring another plate near it, the negative charge is induced. And there are different methods to store electric charges. Maybe this is earth so that we can store more number of charges at a lower potential. So the charge gets accumulated on the surface of the plates, on the plates. And whenever we are connecting it to a power source, this energy gets accumulated. And when we disconnect it from the power source, the energy is released. So we are using it like a source or a battery. That is how we are using a capacitor to store electrical charges. Next, coming to explain the behavior or the magnetic properties of materials. What is the magnetic property due to? Whenever we are taking a magnetic material, it exhibits magnetic properties. But what is the reason for this magnetic property? And this magnetic properties or the behavior of the magnetic substances can always be explained based on electron theory. Based on electron theory. What is electron theory? Whenever you take an atom, you have nucleus at the center and electrons revolving around the nucleus in fixed orbit. So you have electrons in fixed orbits. Now, these revolving electrons around the nucleus, they will behave like magnetic dipole. Because this electron is revolving in a fixed orbit, a current, it will give rise to current. And that gives rise to a dipole. And whenever we are having a dipole, it gives rise to magnetic moment. So, most of the magnetic moment is due to electron spin. Spin of the electron. Here, when we are talking about the electron, just like the earth revolving around the sun and rotating about its own axis, here we have the electron which is revolving around the nucleus and also it rotates about its own axis, which we call it as spin. So, the contribution of the magnetic moment is mainly due to the electron spin, because we also have the spin of the nucleus, which is considered negligible. Now, the next question, what is Curie temperature or define Curie temperature? So, whenever we are taking ferromagnetic materials, up to a certain temperature called Curie temperature, they exhibit ferromagnetic properties. And when we increase the temperature beyond Curie temperature, the ferromagnetic behavior disappears. So I can define Curie temperature as the temperature at which the ferromagnetic behavior disappears. So this is what we call Tc. Tc here represents the Curie temperature. T suffix C. So this is representing the Curie temperature at which the ferromagnetic behavior disappears. Now, Curie-Weiss law. There are two scientists who has given us a very important law relating the Curie temperature and the susceptibility. Chi is equal to C upon T minus Tc. Chi here is what? It is susceptibility. Chi is the susceptibility. And C here represents the Curie constant. C is Curie constant. T is the temperature at which the ferromagnetic material is kept, and Tc is the Curie temperature. This is what we call as Curie temperature. And now when we see this Curie temperature, this temperature is not unique for all materials. So it depends upon the type of material. It is different for different materials. So Curie temperature is not a constant. For a given material, it is constant. But when the material varies, the Curie constant varies, or the Curie temperature varies. Now, coming to the next one, classification of magnetic materials. What is the broad classification of magnetic materials? Now, based on electron spin, materials can be divided into three groups. We are going to divide the materials into three groups: dia, para, and ferromagnetic materials. So how we are dividing them is based on their relative permeability. So if the value of mu r is less than 1, we say the diamagnetic material. And if their permeability is greater than 1, we say they are paramagnetic. And if mu r is much greater than 1, or in the order of thousands, we say it is ferromagnetic. So now what do we understand by mu r? Mu here, r represents the relative permeability. Permeability itself denotes the ability to allow the lines of force to pass through them. So if it is less, then it is diamagnetic. If it is greater than 1, it is para. If it is very high, then it is ferro. Now the next question, sketch neatly the hysteresis loop that is observed in ferromagnetic materials. So what is this hysteresis and how is the loop formed? We will try to understand and sketch the loop. So what is this hysteresis loop? How do we get the hysteresis loop? When the magnetic field induction V varies as a function of H. What is H here? H is the strength or the applied field. Strength of applied magnetic field. And B here represents the magnetic induction. B represents the magnetic induction. Now we know the relationship between B and H. B is proportional to H. Or I can write B is equal to mu H, we have C. This is the relationship. Now what this shows is if the value of H varies, B also varies. Proportional. What we observe here when we are plotting a graph for H versus B. If we are taking H along the x-axis, H is the applied magnetic field along the x-axis, and B, that is the magnetic induction along the y-axis we have taken. And we take a specimen which is not magnetized, unmagnetized specimen we take, and we will start from the origin here. Means at 0. We will bring it and place it in a magnetic field. Then what happens? Slowly magnetism is induced inside the material. Slowly the magnetism gets induced. Means as the value of H increases, the value of B also increases. And then it increases rapidly. Here in this region it is increasing rapidly. And after a certain field, it reaches the saturation point. This is what we call as saturation. What do we understand by saturation here? Is even if we apply or increase the strength of the applied magnetic field, the magnetic induction will not increase. It has reached its saturation. Now at this point, we call this as BS. BS represents the saturation magnetization. At this point, what we do is, we try to withdraw the applied magnetic field. So when we start withdrawing the magnetic field, what we expect is, it should come back along the same direction. This is what we expect. No, when the field is withdrawn, the magnetic induction also decreases, and when the field is 0, the magnetic induction should be 0. But that does not happen. The loop, or what we have here is, it will trace a different path. When we are withdrawing the field, it will go along AC. It is not coming along AO. So it is going along AC. So what this C represents here is, at this point, the field, applied field H is equal to 0. But the magnetic induction is not 0. That is what this curve represents. At this point, we still have some magnetism left in the material. That is what we are calling it as BR. What BR represents here is the residual magnetism. Even after the applied field becomes 0, the magnetic induction is not 0. That is what we have as residual magnetism. Now, to remove this residual magnetism, we apply the magnetic field in the opposite direction, that is minus H. In the opposite direction, we are applying the field. Now, we will trace this curve CD. Now, what happens at D? The value of B is equal to 0. B is equal to 0 at minus HC. This minus HC is the negative magnetic field that has to be applied to remove the residual magnetism. So we call it as cohesive force, HC. Now what we do, we further increase, so we can trace it like this along D, and this is the saturation in the negative direction, and when we further increase the field in the positive direction, we are going to trace the loop like this. So this is how we are going to trace the hysteresis loop. So what hysteresis loop gives us is, we are trying to plot the variation of B with H. That gives us the loop over a complete cycle. Now let us see what is hysteresis. The definition: it means lagging of magnetization B behind the applied magnetic field H. So whatever field we have applied, H and B, if H increases, B increases initially, but it is always lagging behind, because there is H is 0, but B is not 0. That is what shows here, that it is always lagging behind. So that is called as hysteresis. This lagging behind of the magnetization B behind H, we call it as hysteresis. Why this hysteresis, why this lagging is happening is, the energy that we are supplying to the specimen is not fully used. The energy is lost, or whatever is left, it is lost in the form of heat, and we call it as hysteresis loss. So the energy that is supplied, which is not utilized, may be lost in the form of heat, and we call it as hysteresis loss. And this loop or the area inside the loop, it gives us the energy loss, and we are calling it as hysteresis loop. And this happens in ferromagnetic materials below the Curie temperature. We have already seen what is Curie temperature, the temperature at which the ferromagnetic behavior disappears. So below the ferromagnetic material, whenever we are trying to plot H versus B, we are getting this hysteresis loop, and we can calculate the energy loss by calculating the area under the loop. Now coming to the 16th question, define diamagnetic, paramagnetic and ferromagnetic materials. So first we'll see what are diamagnetic materials. Diamagnetic materials are repelled by the magnetic field. So whenever we place a diamagnetic substance in a magnetic field, it gets repelled. And whenever you are placing it in an inhomogeneous field, inhomogeneous means where the field is not uniform. Suppose whenever we are taking a magnet, you see, the North Pole and the South Pole, we have the lines of force like this. These are the lines of force. You may have something like this. Okay. So in this field, when we are placing a diamagnetic substance, it will always move away from the stronger field towards the weaker field. That is the meaning. It is always pushed into the regions of weaker field. Wherever the field is weak, that means it is getting repelled by the magnetic field. And now when we take this diamagnetic material in the form of a rod, and it is freely suspended in a magnetic field, so it turns perpendicular to the field lines. Means if you have a magnetic field like this is the direction of the magnetic field, and we want to suspend a diamagnetic material which is taken in the form of a rod. We have taken the rod. Whatever position you keep this rod, it will always rotate and come perpendicular to the direction of the field. So it turns into a position perpendicular, means at right angles to the field lines. You may place it like this or in any position, but it will always come back to this position, aligns perpendicular to the field. Now coming to paramagnetic materials. What are paramagnetic materials? They exhibit positive magnetic susceptibility. The susceptibility chi is positive. And the magnetization coincides in the direction of the magnetic field. So the magnetization is occurring in the same direction as the applied field. And the value of susceptibility is of the order of 10 power minus 6, which is small. And the relative permeability mu r is slightly greater than 1. Mu r is slightly greater than 1. And field lines are pulled towards the material. So what do you mean by field lines are pulled towards the material? So whenever we are taking a magnet, north and south, there will be field here. And if we are placing a paramagnetic material, the field lines are pulled towards the material like this. Otherwise, they should have been like this. But they are pulled inside the material. So, field lines are pulled towards the material and permeate. Permeate means pass through it when placed in the magnetic field. Now coming to ferromagnetic materials. Ferromagnetic materials, they exhibit high values of susceptibility and permeability. Their permeability, relative permeability is very high, of the order of thousands, and the value of chi is also very high. Susceptibilities are of the order of 10 power 6. And relative permeabilities are of the order of few thousands. And when a ferromagnetic material is kept in a magnetic field, the field lines will crowd into the material. Means they exhibit strong attraction. So the North Pole we take and the South Pole, and if this is a ferromagnetic material, all the field lines will pass through the material. That is how they are crowded. That is what we say, field lines crowd into the material. And when we take it in the form of a shell, all the field lines will concentrate inside the shell without penetrating into the cavity. They will not go into the cavity, but they are inside the shell only. Now coming to the next question, give some examples of diamagnetic, paramagnetic and ferromagnetic materials. So diamagnetic materials, the examples are bismuth, zinc, water, or that is gold. All these are examples for diamagnetic materials. There are many but few. They have asked us to write any 2 examples for each. So the paramagnetic is aluminium, platinum, manganese, copper chloride. These are few examples for paramagnetic. And for iron, for ferromagnetic we have iron, nickel, cobalt, etc. Now the next question is define retentivity and coercivity. What is retentivity and what is coercivity? So we will explain these two with the help of the hysteresis loop. We have already discussed about the hysteresis loop. So what this hysteresis loop tells us about is the lagging behind of the magnetic induction B to the applied field H. H is the applied field and B is the magnetic induction inside the ferromagnetic material. So as the applied field increases, the magnetic induction slowly increases, then rapidly, and reaches the saturation point. But when we are withdrawing the magnetic field, it traces a different path, that is AC. And this point C here is the point of discussion. So what is happening at C? At this point, the applied field H is equal to 0. H is 0 here, but B is not 0. Means even when the applied field is withdrawn, there is still some magnetism left in the material, which we call it as residual magnetism, BR. BR is the residual magnetism. And this power of retaining the magnetism, we are calling it as retentivity or remanence. Remanence or retentivity, both mean the same. What they tell us about the power of retaining the magnetism, that is called retentivity. Now, in order to remove this residual magnetism, we apply a negative field. So we are applying the field in the negative direction, minus H. So we trace the curve along CD. So what is the value of B at D? At this point D, B is equal to 0. Means at a particular field, applied negative field, the value of B becomes 0. And this applied field, we call it as coercive force, or it is coercivity. The property we are calling it as coercivity. Now the next one is, what is Bohr's magneton? Bohr is the name of the scientist. And he gave us a constant, which we call it as Bohr's magneton. So this comes from the formula for orbital magnetic moment. What is orbital magnetic moment? When an electron is revolving round the nucleus, because of its orbital motion, it produces the dipoles, and because of that we have the magnetic moment. And the magnetic moment is denoted by mu L. Mu generally represents the magnetic moment and L here denotes it is due to the orbital motion. So mu L is equal to minus E by 2m into LH by 2 pi. Minus E by 2m into LH by 2 pi. So what is E here? E is charge of electron. E is the charge of electron, which is a constant. 1.6 into 10 power minus 19 coulombs is the charge of electron. And m here is the mass of the electron. We may write it as me or simply m. So m here is what? Mass of electron. And mass of electron is constant, 9.1 into 10 power minus 31 kilogram. H is also a constant. What is H? H is the Planck's constant. H is Planck's constant and its value is 6.625 into 10 power minus 34 joule seconds. Now, if you see in this, 2 is a number, 2 pi is a number. So, E by 2m, 2h and h, all these are constant. Only thing varying is L. So, I can just write it as EH by 4 pi m into L. So, all these values inside the bracket, they are constants. So, we can simplify and write it as Bohr magneton, which is denoted by mu B. So, I can write mu L as mu B into L. What is mu B? Mu B is nothing but Bohr's magneton, which is given by EH by 4 pi m, whose value is constant. When we simplify, we substitute all these values and simplify, we get 9.27 into 10 power minus 24 ampere meter square. So, this is the value of Bohr magneton. Then the last question, relative permeability values. What will be the relative permeability values for diamagnetic, paramagnetic and ferromagnetic substances? For a diamagnetic substance, mu r is less than 1. It is positive, but its value is less than 1. And for paramagnetic, mu r is slightly greater than 1. So, we can write mu r greater than 1. And for ferromagnetic, mu r is of the order of hundreds and thousands. So, I'll write much greater than 1. So, this is a comparison of the relative permeability values. Diamagnetic mu r less than 1, paramagnetic mu r greater than 1, and for ferromagnetic it is much greater than 1. So, for more understanding of the answers or to get answers for these questions from the question bank, you can refer to these reference books. Introduction to Electrodynamics by David G. Griffiths. And also you can refer to Concepts of Physics by H.C. Verma. And Unified Physics, Electricity, Magnetism and Electronics by Dr. S.L. Gupta. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.